Hi, this is Barrett Givens, and in this video, we're going to talk about some of the basic properties of closed sets in a topological space. So recall that the definition of a closed set in a topological space is that a set A is closed if and only if its complement is open. So if you want to use the definition to tell if a set is closed, you just have to take the complement of the set, figure out whether the complement is open, and if it is, then you know your set is closed. Okay? And the fundamental theorem about closed sets kind of says, how they can be combined. So this is the theorem. Let X be a topological space. First of all, the empty set and X have to be closed sets. Secondly, if you have a whole bunch of closed sets, it could be a finite number of closed sets, an infinite number of closed sets, a bunch of closed sets indexed by anything. Any intersection of closed sets has to be closed. And then if you have a finite union of closed sets, that also has to be closed. So this theorem should maybe remind you of something that you might have seen before. It's got these three properties, one about empty set and the whole space, one about intersections, and one about unions. And that reminds me a lot of the definition of a topology, which is really the definition of what are open sets. So we have this definition of how sets can be considered open, and now we have sort of a similar definition with closed, but it's a little bit different because if you remember with open sets, we could take any union of open sets, any union of open sets. But here we have any intersection of closed sets. So any union of open sets is open, any intersection of closed sets is closed. And then when we were thinking about open sets, we could take finite intersections of open sets, but we can take finite unions of closed sets. So it's like the words union and intersection kind of got flipped, right? Why would that be, I wonder? Is there a reason? I think there is. Okay. So let's talk about it a little bit. I'm going to go ahead and prove the second of these three properties. The first one, I think maybe we can just talk through. Empty set and X are closed. Well, why would that be? Well, imagine that you're looking at the empty set. You want to know if it's closed or not. Well, you take the complement of it. The complement of the empty set is all X. It's the whole space. Is X open? Yes. So since X is open, empty set is closed. Okay, you can make a similar argument for X. All right, let's do the proof of part two. Proof of two. Okay, we want to take an intersection of closed sets, and we don't know how many closed sets. It could be 2, 3, 5, infinity, an uncountable number. It could be any number of closed sets. So I'm just going to write this in a very abstract way. I'm going to say let F sub alpha for alpha in I be a collection of closed sets. So I is my index set. I could be, just 1, 2, 3. I could be the natural numbers. I could be the real numbers. I could be anything. Okay. But the point is just that I have a whole bunch of F sub alphas where alpha takes on a range of values. Who knows what the alphas are? And then let's let F be the intersection of all of the F sub alpha. All right. So first, what do we know about each F sub alpha individually? Each F sub alpha is closed. So by definition of closed, F sub alpha complement is open for each alpha. Okay. And that's about as far as we can go with that hypothesis. Now, we want to look at capital F. We're trying to prove capital F is closed. So to see if a set is closed or not, we have to, again, go back to the definition of closed. We have to look at the complement of capital F. So F complement is the intersection of the F alphas complement. So what did I do there? I just took the thing that F equals and I just sort of subbed it in, okay? And now, how can I simplify that? I have an infinite, possibly infinite intersection, and I'm taking the complement of it. There's some laws that tell us how intersections and unions and complements all sort of interact. So this tells me that F complement is the union of F alpha complement, and that is De Morgan's laws. Okay. Now, what form does this have? Each F alpha complement is open. I know that each F alpha complement is open. So this is a union of open sets down here. This is a union, and these sets are open. And so F complement is thus a union of open sets. And we know from the definition of a topology that any union of open sets is open. So F complement is open. By definition of closed, F is closed. So I started with a collection of closed sets, F alpha. I formed their intersection, and then I showed that their intersection is closed. And so therefore, I've proven number two. Any intersection of closed sets is closed. All right. So I think you might see there, what was it that happened that the definition of topology says any union of open sets is open, but then this theorem says any intersection of closed sets is closed. Why did union turn into intersection? It's because when you take complements, intersections turn into unions because of De Morgan's laws. And then vice versa, when you take complements, unions turn into intersections, right? Complements and De Morgan's laws kind of say that unions and intersections kind of switch, is the way to think about it. All right. Thank you so much for listening.